Welcome to This Explainer. Today, we're tearing into the scientific method. And look, I know what you might be thinking, but no, it's not just some static, boring list of facts you had to memorize in middle school. It's actually this incredibly active, systematic process we use to investigate deep questions, solve super complex problems, and really uncover the truth about how our world actually works. Basically, it's the ultimate playbook that researchers use to structure their inquiries and make those massive, groundbreaking discoveries.
Okay, let's just dive right into our roadmap for today. We'll be hitting 6 main stops. The ultimate discovery tool, observe and ask questions, formulate an educated guess, designing the experiment, gathering the evidence, and finally, reaching a conclusion.
All right, Section 1, the ultimate discovery tool. We are kicking things off by looking at the big picture of how scientists actually investigate problems and answer questions, without just relying on blind guesses. So the scientific method is what ensures our investigations are organized, fair, and literally 100% based on evidence. It's a completely linear 6-step playbook. We move sequentially from observation straight into question, then hypothesis, through the experiment, into data collection, and finally to the conclusion. Sticking to this exact sequence, that's the secret sauce. That is exactly what separates a random shot-in-the-dark guess from a true scientific inquiry.
Moving right along to Section 2, observe and ask questions. Because honestly, every single great discovery begins with simply noticing the world around you.
Now, observation isn't just taking a quick glance at something. It means carefully, intentionally noticing and describing events or phenomena using your senses, or of course, scientific instruments. For example, picture this. You notice a plant sitting near your window, and it seems to be growing noticeably faster and leaning directly toward the sunlight. Just that simple act of noticing, that is the foundational spark of the entire scientific method. It pinpoints a problem and gives you the base for your whole investigation.
But here's where it gets really interesting. There's a vital contrast between the two main types of observations we make. On one hand, we've got qualitative observations. These describe characteristics or qualities you can't easily count, like noticing a flower is red, or maybe a leaf feels rough to the touch. On the flip side, we have quantitative observations. These involve hard numbers and measurements. So instead of just saying, wow, that plant is tall, you actually measure it at exactly 25 centimeters. Both are absolutely crucial, but they serve completely different analytical purposes.
Naturally, those initial observations practically force us to ask a question. And in science, this question has to be clear, it has to be specific, and most importantly, it has to be testable. So, looking back at our plant on the windowsill, we can formulate a really tight, focused question. Does sunlight affect plant growth? It sounds simple, right? But that single sentence is going to guide our entire investigation, giving us the exact focus we need to accurately measure our results.
And that brings us to Section 3, formulate an educated guess. Because once we have our driving question, we've got to make a prediction before we actually start testing.
Enter the hypothesis. A hypothesis provides distinct direction for your investigation because it predicts a highly specific outcome based on your previous observations and whatever existing knowledge you already have. It is, quite literally, an educated guess. But here is the kicker. To be effective, a hypothesis absolutely must be something that can be accepted or rejected based on the evidence you're about to gather. If you can't test it, it's not a good hypothesis.
Let's look at a pretty perfect example of a testable hypothesis for our running plant scenario. If plants receive more sunlight, then they will grow taller. Notice how beautifully that works? It directly answers our previous question while setting up a crystal clear condition and outcome. We've officially set the stage to see if our educated guess is on the money.
All right, Section 4, designing the experiment. With our prediction locked in, it is time to build a carefully planned procedure to actually test the thing out.
Now, to determine cause and effect, any good experiment relies on strictly defining 3 different types of variables. First up, the independent variable. This is the single factor that the scientist deliberately changes. Next is the dependent variable. That's the factor you're measuring to see the result of that change. And finally, the controlled variables. These are the factors you keep exactly the same across the board throughout the whole experiment to make sure the test is totally fair and reliable.
Applying this to our little plant mystery really brings these concepts into focus. Say we put one plant in the sun and one in the shade. The amount of sunlight, that's our independent variable. The height of the plant at the end of the experiment, that's our dependent variable, because that's what we're measuring. But to make this a fair fight, we have to strictly control the other factors. We use the exact same amount of water, the exact same type of soil, and identical plant species for both. By locking down those controlled variables, we know for sure that any changes in the plant's height are caused strictly by the sunlight, no other sneaky factors involved.
Let's jump into Section 5, Gathering the Evidence. This is where the rubber meets the road. We run the experiment and carefully record our findings.
Just like our initial observations, the evidence we gather here works in a very similar way. It can be qualitative data, which is descriptive, like noticing the water turning cloudy or a leaf shifting from green to yellow. Or it can be quantitative data, which gives us hard numerical information, like a final mass of 50 grams or measuring our plant at exactly 30 centimeters tall. Accurately gathering this evidence is what allows us to spot reliable, undeniable patterns.
And here is the quantitative method in action. By logging our dependent variable, which is the plant's height in centimeters, on specific days, we take raw numbers and organize them into something meaningful. Looking at the progression here, going from 10 centimeters on day 1 all the way up to 25 centimeters on day 15, we've identified a clear, undeniable pattern of growth to use for our final judgment.
Finally, we arrive at Section 6, reaching a conclusion. This is the big payoff where we interpret those results and draw our final findings.
By analyzing our data table, we successfully answer our research question. The results show us that the plant in the sunlight absolutely grew taller than the plant in the shade. Therefore, our hypothesis was supported by the experimental results. Our initial educated guess was right on the money. This conclusion summarizes our findings and lets us make informed decisions based purely on empirical evidence.
But what if our data had completely contradicted our educated guess? What if the plant in the shade actually grew taller? Well, it's so important to remember that a hypothesis is not considered a failure if it's rejected. Honestly, this requires a pretty big shift in how we traditionally think about being wrong.
Discovering you were wrong isn't a failure at all. It's actually the stepping stone to repeated testing and real scientific progress. If a hypothesis is rejected, it just means you've learned something new. Scientists will simply take that information, revise the hypothesis, conduct further experiments, and collect more data. This endless cycle of curiosity and refinement is exactly what ensures our investigations get closer and closer to the truth, no matter the outcome.
So now that you hold this ultimate discovery playbook, I really want you to consider how you can apply it. Science isn't just confined to some fancy laboratory with white coats. It is a systematic way of problem solving that you can use every single day. Whether you're troubleshooting a super annoying Wi-Fi network issue, diagnosing a weird rattling sound in your car, or trying to perfect a really complex recipe, you can utilize this exact same analytical process. So I'll leave you with this. What everyday mystery will you investigate next using observation, hypotheses, and controlled experiments?